Hello, my name is Ahmed Musaafir, and in this presentation I'm going to talk about our work on a sampling-based tool for scaling graph datasets. To give you a little bit of context about this work, graph datasets are being increasingly used, and consequently graph processing has also become an interest in many different domains. There are many different graph processing platforms out there that can be used to analyze these graphs, such as Giraph or GraphMath, and these platforms often include popular graph algorithms like breadth first search and provide a framework for writing your own algorithms. Existing studies show that the performance of graph processing depends on different variables: the platform, algorithm, dataset, and the underlying hardware. For example, if you have the same platform, algorithm, and hardware, but use a different dataset similar of size, you'll get a different output in terms of performance. But the reason why there is a difference is not clear, and this is caused by a difference in the intrinsic properties of the graphs. To illustrate this a bit better, this figure shows the results of an experiment where we measured the throughput of BFS in edges traversed per second running on a family of correlated graph datasets generated using the Graph 500 generator and uncorrelated graph datasets obtained from public graph repositories. All these results are presented in the increased order of the graph sizes. Notice that for the uncorrelated datasets, the larger graphs do not necessarily perform worse than smaller graphs, but for the correlated datasets, the performance can actually correlate with the properties of the graph from a family of which multiple properties can be controlled. And to be able to do an in-depth performance analysis or evaluation, to get a better understanding of why these differences occur from the properties of a graph, or even get a better understanding of the performance issues, you'll need to have representative datasets. However, this is where our problem comes into play, as there is a lack of representative graph datasets. Now, there are some synthetic graph generators out there that can be used to generate the graph from scratch, but they generally don't allow you to control the properties of the graph, and if they do, they only allow you to control specific graph properties only, focusing on generating specific types of networks. There are also some existing graph archives available that provide some few types of graphs, but these generally are quite small and they do not meet the criteria that is required for performance analysis. Therefore, in this work, we tackle the need of more and representative datasets specifically for graph analytics benchmarking by scaling an input graph as seed to generate families of graphs. We have constructed models and guidelines that predict the properties of scaled-up graphs to allow certain graph properties to be preserved or tuned. Lastly, we provide an open source tool where we implement our method to generate diverse families of graphs. In essence, our tool accepts an input graph, a scaling factor, and several additional parameters which will be introduced later in this presentation to obtain a scaled graph that is smaller or larger than the given input graph, with properties adjusted according to the given input parameters. Now, when it comes to scaling down, there already exists work on graph sampling to obtain a reduced representative sample from an original graph. These sampling algorithms can be generally put into three main categories: node-based, edge-based, and traversal-based sampling. And the sampling algorithms generally try to preserve as many properties of the original graph as possible, or focus on preserving certain properties of the graph. The properties we are talking about are local properties of the graph, such as the clustering coefficient distribution, and topological properties like the shortest path length or connectivity of the graph. In our work, we have analyzed these 5 popular sampling algorithms and their claims for property preservation, and we have summarized these results in this table. Totally induced edge sampling, or TIS, has shown to preserve the majority of the local and topological properties of the graph, and in our scaling down and scaling up method, which uses sampling as its score, we have selected this algorithm mainly due to its superiority, and we will show the experimental results using this algorithm accordingly. However, it is important to keep in mind here that these qualities do not always apply, as the dataset that is used could also affect some of these qualities for the better or worse. The sample size can also affect the quality of property preservation, and generally a larger sample size preserves the properties of the original graph more. Furthermore, we must note that the exact scale of the sampled graph is based on either the fraction of desired vertices or edges, and this depends on the sampling algorithm that is being used. And we will clarify this a bit more in the results. All the sampling algorithms shown in this table have been implemented in our tool and can be used for scaling purposes. Let's have a look at some of the results for scaling down a graph using totally induced edge sampling. This is the original COM-ORCID graph with some of its properties shown accordingly. If we have a look at a scaled down version that uses a sample size of 0.8, we can see that the number of nodes corresponds with the size of the sample, but the number of edges is significantly higher than a 0.8 sample. And this is caused because TEAS oversamples the edges during its total induction step. And because of this oversampling, the degree and density are higher. Note, however, that the diameter, average clustering coefficient, and average shortest path remain similar to the original graph. The graph, however, lost its connectivity when being sampled by TEAS. And as we reduce the sample size, we seem to move further away from the original values of the graph. Overall, the properties that are preserved reflect the qualities of TEAS. For scaling up, existing work lacks mechanisms for controlling properties of diverse input graphs. The diversity of graphs produced by graph generators like Graph 500 is very limited, and these have to be generated from scratch. There are also some existing graph evolution methods that focus on generating a later version of the same graph, but these also lack the diversity and focus on some type of graph networks only. Finally, there are some existing graph scalers like Gscaler that do allow users to provide an arbitrary input graph, and these tools can produce more diverse graphs than generators because of this ability. However, these often want to preserve the properties of the original graph and do not allow any control over them, whilst the ones that do offer this are limited in this control or suffer from performance issues. Instead, our goal is to provide several larger versions of the same graph quickly, regardless of the domain of origin of the graph, and where we also have certain control over the properties. At the very core of our scale-up method lies graph sampling. We scale up a given graph by first obtaining samples of the original graph based on the scaling factor and sample size. If our sampling algorithm is random, we would obtain different samples of the original graph rather than the same one. And after the sampling phase, we would then interconnect these different samples accordingly. As an example, let's say we want to scale up a given graph 4.5 times. If we assume that we use a sample size of 0.5, we would obtain 9 different samples of the original graph, which we can then interconnect in some way. This method brings different parameters that we can further provide as an input to the user. The user can select between different topologies to interconnect these different graph samples together. Currently in our tool, we provide the option to select between a star, chain, ring, and fully connected topology. Additionally, the user can also specify how the vertices between two samples are selected. Currently, this can be either random vertices from each graph or high-degree vertices. Lastly, the user should also specify the number of edges between every sample, and also whether directed edges or undirected edges should be used. All these different parameters can be used as an input to the graph scaling tool to obtain a scaled-up version of the graph. All these different parameters that were just presented can all affect the properties of the output graph, but it is also important to keep in mind that the choice of sampling algorithm and subsequently the sample size can affect these properties. We know, for example, that using smaller sample sizes do not preserve the original properties of the graph. The scaling factor may as well affect the properties of the output, as well as the dataset that we are scaling, because the qualities of the sampling algorithm are propagated here as well. So how do we measure the quality of the scaled-up graph? The properties of the scaled-up graph should be somewhat predictable based on the same input parameters, and we provide models and guidelines that can guide the user to obtain a certain graph based on these. For example, if the user wants to obtain a scaled-up graph with a larger diameter, choose a chain topology with a single random edge, and the graph output should adhere to these models and guidelines. Let's now look at some of our scale-up results. And in all of the results that will be presented here, we have used a scaling factor of 3 with totally induced edge sampling and a sample size of 0.5 for all the scale-ups. This would essentially result in having 6 different samples. This is the original Facebook graph. Let's see what happens to the properties when we scale this up using the star topology using random bridge vertices and one single interconnection. Notice first of all that we have about 3 times as many vertices, but more than 3 times the amount of edges. And just like with the scaling down results using these, this is caused by this oversampling of the number of edges. And because we have 6 different samples, all of these oversampled edges add up together. Had we used forest fire as a sampling algorithm, for example, we would have hit the desired number of edges, but we wouldn't have had any control over the number of vertices. Notice our graph became disconnected, but our diameter nevertheless grew, although it of course stayed below the limits of the star topology structure. If we keep the same parameters but only use the chain topology, we can see that this caused the diameter to increase much longer. For the fully connected topology, this became shorter as each graph sample was connected to one another. Now if we look at what happens when we switch back to a star topology but increase the number of interconnections to 45,000, aside from the diameter and shortest path dropping significantly, the average clustering coefficient has also dropped. Whilst if we keep the same parameters but only use high degree bridges instead of random, the average clustering coefficient gets increased more. Another interesting result is that if we look at the shortest path distribution, where we only use different topologies, we see that the chain topology has the longest number of hops, followed by the ring, star, and fully connected topology. And all these results adhere to our models and expectations. Now, similarly as how Graph 500 can generate families of graphs, our tool can be used to generate families of scaled graphs that can be subsequently used for performance analysis. We conduct 2 case studies where we analyze how the properties of the scaled-up graphs impact the performance of 2 graph processing algorithms. More specifically, we measure the processing times of breadth first search and PageRank using GraphMath as a graph processing platform and the Graphalytics benchmark suite. And we conducted this case study using 2 datasets that are available in public graph archives, but will only show the results for ComLife Journal for the sake of time and because we observe similar performance trends for the 12-month one graph. Now all the scale-ups conducted in these case studies use a sample size of 0.5 and random bridge interconnections between the different graph samples. With those fixed parameters, we use a combination of different scaling factors, topologies, number of interconnections, and different sampling algorithms, as well as graph copies. For sampling, we selected these mainly because of its superiority when preserving properties, and forest fire to preserve the connectivity of a graph during sampling. Now, the reason why we also decided to use full graph copies instead of sampling algorithms is to merely observe the effects of the other parameters, regardless of the sampling algorithm. Note that we also use a scaling factor of 8 for graph copies, and this is because the topologies and interconnections for a scaling factor of 2 are all equivalent. Let's have a look at some of our results. This figure shows the normalized runtime of BFS based on the scaling factor. The runtime of this algorithm on the original dataset is represented by this horizontal line. This legend shows the different types of scale-ups that we have performed using forest fire as a sampling algorithm. and the bars in the figure show the runtime of BFS on these different scale-ups accordingly. Notice here that the runtime is the longest whenever we use the chain topology, as these graphs have the largest diameter. However, as we add more interconnections, the diameter drops and the runtime of BFS is faster, and this holds for all the topologies. Note that the performance numbers of all these scale-ups for BFS reflect the number of hops from the plot presented earlier. If we use T's sampling algorithm for the different scale-ups, the runtime of BFS increases, and this is likely caused by the oversampling of edges in T's during the total induction step. Let's now see what happens when we use graph copies instead of a sampling algorithm, but note here that we have also included a scale-up of 8, since a scale-up of 2 is similar across all the topologies and interconnections. Here we can observe that the runtime is generally lower than when using a sampling algorithm. Between all three scale-ups using different sampling algorithms, we can see a similar performance trend based on the topology and number of interconnections. Another thing that can be observed here is that the fully connected topology scale-ups with many interconnections have a roughly linear scalability. Notice the variety in the runtime between each scale that can be produced by these different graph families. And to quickly go through PageRank, in contrast to BFS, adding more interconnections does not reduce the processing time necessarily. Lastly, note here that when using graph copies, the chain topology and fully connected topology have a much higher runtime. To summarize, our case studies demonstrate a useful degree of control on the properties of scaled graphs and how different properties of performance correlation hypotheses can be verified using our graph families. These case studies provide a first step towards an approach based on systematic sensitivity analysis to build performance models parameterized by graph properties. The full experiment setup and case studies is provided in our paper, where we also refer to the actual performance numbers. Now, regarding the implementation of our tool performs faster than most existing tools, even when running on a single node. But we also have a parallel and a distributed version available, which focuses mainly on speeding up the sampling phase, as this dominates the overall execution time of the scaling operation. We also provide an auto-tuner that tries to find a proper match between the desired value of a property and the models. At this moment, this has been only implemented to find a desired given diameter. Our tool is publicly available in our repository, where we also provide additional results and performance numbers. To conclude this presentation, in order to tackle the lack of representative datasets for benchmarking, we have provided a pragmatic solution, which is a sampling-based method for scaling existing graphs to obtain a family of similar graphs with certain properties that can be controlled depending on the user requirements. We have validated our tool on a set of different graph datasets, and our empirical analysis shows that generating diverse graphs with predictable and controllable properties is feasible. Our case studies demonstrated that diverse graph families provided by our tool can be used for uncovering the behavior of graph processing platforms. Thank you for taking the time to listen to this presentation, and if you have any questions, please let us know.